In the previous session, we stopped off with saying that that there is something called a buffer overflow, which I want to basically start talking, because this buffer overflow that I am going to cover in this particular session, the next two sessions, is an example of a vulnerability in which there is a participation from the compiler, there is a participation from the operating system, and there is also a participation from the architecture. So, the architecture, operating system and compiler collectively is responsible for one vulnerability, and that is what I am going to present in the next two sessions. So, in this session, as I told you and I assured you that this course is extremely self-sufficient, you need not have any prerequisite, of course some basic programming that I hope everybody knows. I will now talk about function calls and stacks, right, which is a very preliminary subject, but to have a completeness and also revise if in case some of you have forgotten, I will now talk about function calls and stacks in this particular session 3, right. So, what is function call? The function call is very important for software development. Why is function call very important for software development? Because this gives you a modular approach to developing software. A software reuse is also possible because of function calls, correct? You write a function and that function can be reused by somebody else. That is how libraries have come up. Your math.h, your even stdio.h, everything are all libraries that are developed by someone which you are using. So, function calls are extremely important for software development. Then there are two, and in a function call there are two fellows, one is a calling function, another is a called function. And there are two ways by which you can call a function. So between a calling function and a called function there is some communication that needs to happen. The calling function actually sends certain parameters to the called function. Based on those parameters, the called function evaluates something and returns back a value. And this return back can happen the way by which you pass the parameters. You can pass the parameters either by reference or by value. A very simple example of passing by reference is your scanf, where you go and say, go and store the value that you are reading in a particular location. So, in this case, myvar, as you see, is a variable, it is an integer variable. When I say ampersand myvar, it gives the address where that myvar is stored, right. So, I pass that address to the scanf. So, whatever I am reading there, that integer what I am reading there is gone and stored in this address. So, when I come back out of scanf, I go and access that myvar location, I will get the value of that variable. You get this? When I am printing a value, I have to tell what to print. So, there is no need for an address. I just send the value and it goes and gets printed. So, printf %d myvar actually takes the value of myvar and gets it printed. So, these are the two ways by which I could pass parameters between a calling function and a called function. So, the function actually returns, many of the functions return certain values. Even the printf actually returns a value, scanf also returns a value. Do you know what value scanf returns? Huh? Okay, the number of variables that are basically read out. Now, the most important thing is when I call a function, it does certain things, it starts executing. So, I am a calling function, when I call a function, it starts executing and then it gives back me the answer, right. And when I get the answer, I should start executing from the point where I left, right. So, the most important thing is the context of the calling function has to be retained for continuation after the called function finishes, right. So, that is very important and that is where the programming languages have grown. They they give you an infrastructure by which you can call a function, the function will get executed and then you return back and you start from the point where you left. So, there are certain variables that may get manipulated because of this function call, but all the remaining variables should have their own value and I should be in a position to start from the point where I left. Are you getting this? And that is very important. And to maintain this context, a stack, a data structure named stack is used. The stack follows a very simple policy called first in last out policy. Whatever I push first, that will come out last. So, if I push A, B, C and what you call the other operation pop, I will get C, B, A in the opposite arrow. And this first in last out model or last in first out model, both means the same, okay, suits the function call model as follows. Why it suits that? This is how. So, look at this slide. On the right hand side you see a stack, right. The blue color what you see is a stack. I hope all PowerPoints, all cameras show it as blue, okay. So, the blue color you see is a stack and there is one small arrow on the top which is called the top of the stack. This is where you start pushing in some things into the stack. So, the initial state of the stack is that nothing is there in the stack, and now I am going to execute the program that you see on the left, right. So, there is a main routine, there is a main function and it has 3 variables AM, BM and CM, and then it calls a function called myProc and it passes 2 parameters into it, namely AM and BM. That myProc executes something and it will return an integer back which is stored back in BM. Inside myProc again it has 2 input parameters EM and FM, what you see in the red color there, and then it has 3 integer variables AM, BM and CM inside that. It calls another function what we call it as next sk1. It passes 2 parameters. Next sk1 actually again has 2 input parameters and some variables. It does some computation and it returns a value. So, main calls myProc, myProc calls next sk1, next sk1 executes, it returns back. Once it returns back a value, it returns back to whom? It returns back to myProc. That value returned by next sk1 is assigned to BM and then your myProc starts executing. Please see the red there. myProc starts executing from L2, it does some computation and it returns a value. That return value goes to the main routine which is assigned to BM again there, and now the main routine starts executing from L1. So, are you getting the context of this? So, what happened? Main called myProc, myProc called next sk1, okay, right. So, who was first fellow? Main went in, starts executing first, then myProc starts executing next, then next sk1 starts executing last. Who finished first? Next sk1 finished first, then myProc finished next, then main started executing and it will finish last. So, that is why the fellow who starts executing first finishes the last in the context of functions, and that is why we call it as a last in first out policy. And since it is last in first out, I can use a stack basically to execute this function, okay. Now, what happens here when I start executing this? Please note that when main starts executing, let us say before it calls myProc, before main calls myProc, the value of AM, BM and CM are 2, 1 and 1. So, in the stack on your right hand side there are locations reserved for AM, BM and CM of main, and there you see 2, 1 and 1. Now, the function call happens, myProc is being called, automatically what happens? The hardware, the architecture loads the return address, namely L1 here, because after myProc finishes execution, your main should start resuming from L1, right. So, that L1, that return address is basically stored in your stack. Who does this? The compiler just compiles an instruction called call. The call, when it is executing in the architecture, the architecture loads the return address. The architecture loads the return address. So, who is responsible for putting that L1 there? Architecture. And then the 2 parameters that are passed, namely AM and BM, that is 2, 1 is also now loaded into the stack. Now what happens? Your myproc starts executing. So where will myproc gets the value of the parameter? It is already there in the stack. So that is why there is something called FP, which we call it as the frame pointer, and there is SP, which you call it as the stack pointer, right? The frame pointer points to where the variables for the current routines which has come from the calling function are stored. So FP points to 2 and next is 1. Now the stack pointer is pointing to the next empty location there. Now myproc starts executing. So the myproc gets the value for those 2 input parameters, the EM and FM you see on the red on the left hand side, the red part, that values are 2 and 1. Okay. Now myproc starts executing. Now what happens there? Myproc as an AM, it has a BM and it also has a CM. So so AM takes a value 3. BM is not assigned, it is having a value junk, it can have a value j. Then CM has a value 6. So before myproc reaches nest sk1, so these are all the values for all its local variables. So there are 3 local variables for myproc, AM, BM and CM, and those are also getting loaded into the stack. Then now it passes 2 values to, now it calls nest sk1. The moment it calls nest sk1, the compiler will compile it as a call, right? The assembly language instruction is called call. That call will execute and your architecture will now load what? The L2, the return address, that is after my next sk1 completes, where should I start executing? That L2 is loaded into the stack, then 3 and 6, the parameters that are passed for next sk1 are also loaded into the stack. Right, and now nest sk1 executes. Now nest sk1 takes 3 and 6 and it will return the value 18. Okay, so it returns the value 18, and where it will return the value? It will return the value back to the same stack. Now when you return, now what happens? The control goes back to L2. Where do you get the value of L2? It is already there in the stack. So I take the value of L2 from there, and before starting executing I have to make BM as 18. Note that in the stack BM has actually become 18, which is the return value from nest sk1. Now the program will start, the next proc will, myproc will start executing from L2 now, right? Now what happens here? So BM is 18, AM is 3, so your CM now should become 21, right? So the answer is again stored back into the stack by myproc. So if you see on the stack on your right hand side, you have 21. Now what happens here? Now your program starts executing from L1, right? Because the address is there. So what has happened now? So when we just quickly see this before we wind up this session, what has happened now is as follows. At every point when I call a new function, the moment a function is called, there is a frame created for this. This is called a stack frame, right? In that frame, all the variables, all the local variables are basically given some place where you can go and store the values of these local variables. You are getting this? And then and as I go to the next function, these local variables are not touched. The next function works on its own stack frame, and after it finishes it just passes the value back to the previous stack frame. So if I quickly go back, so this is the stack frame created for main, and when myproc executed, there is a new stack frame created for myproc. This myproc is not touching the stack frame of the main. So all those variables there remain untouched. So when myproc completes and goes back to main, except for the variable that that is going to be returned by myproc and that is going to be manipulated by myproc, which is BM, all the other variables, the values are remaining same, right? You understood this? This is how stacks and function calls work. And why should I need such an infrastructure, right? Because see, please note, I have made one careful decision here. I have made one very interesting thing here, that I have named all the variables same in all the 3 functions. Most of the variables are same. So the AM of main is different from the AM of myproc, which is different from the AM of nestsk1. Why is this important? Because otherwise, if I say every function should have its own distinct name, then I can't reuse. So I say I will use your function only if you don't use the verb name AM. So everywhere you put some Aadhaar ID in your, hopefully it is unique, and write your variable names, right? Can I do that? We can't do that. So this gives you independence. In some sense, it is isolating the execution environment of myproc from the execution environment of main, right? It isolates your nestsk1 execution environment from myproc from main, right? As and when I keep calling functions, what is happening here? Every new function is working in isolation without touching the other functions, and this is how function calls are executed. Now, one another thing before I wind up this session, I should basically tell you that I am using the same stack, right? And why I am using the same stack in this environment? I am using the same stack because I want that function to communicate with me, and I am using the stack as a medium for the called function to communicate back to the calling function, and the calling function to communicate to the called function. How do they communicate? I send you variables and you send me the result. I am the calling function, you are the called function, and I use a stack as a medium for this communication, as you have seen here. So with this small input, I wind up this session and we will go to the next session.